So the last part of this section is projection and a little bit about work. So let's talk a little bit about projection. So again, you should have read this in this section, but let me just remind you the projection of vector u onto v is given by the formula projection of u onto v is u dot v over magnitude of v times v over magnitude of v. Now you can write this a little concisely as u dot v over magnitude of v squared, times vector v. And you should have read in the notes, since we have this formula for the dot product, we could replace this with u magnitude of u times magnitude of v over cosine of theta times cosine of theta, over magnitude of v times v over magnitude of v. And now canceling, that gives me magnitude of u times cosine theta times v over magnitude of v. Okay, and so this constant here that we're multiplying by the unit vector that we formed here, this is called the component of u in the direction of v. Okay, so that's just a recap of what you should have already read in the textbook. Let's go through a couple of examples that again are in the book, but I just want to make sure that you see them again. So this first one I want to look at is example 6 from the book. So I want to find the projection of u onto v and the vector component of u orthogonal to v for the vectors u equals 3i minus 5j plus 2k and v equal to 7i plus j minus 2k. All right, so I want to switch to GeoGebra for a second just to look at these vectors. Oops. All right, so I've already put in the points here, A, B, and C, where B and C are just the endpoints of my vectors u and v. So here is vector u in blue, and here is vector c in red. Our x-axis is here in the red, and y is in green. Z is pointing up. So there are my two vectors. Remember, the projection of u onto v, you want to think about taking and casting a shadow, the shadow of u onto v, okay? All right, so let's compute it with the formula, and then we'll come back and see what that looks like in the picture. So my formula says the projection of u onto v is u dot v over the magnitude of v squared times v. So u dotted with v, I'm going to get 7 times 3 is 21, plus negative 5 times 1, so minus 5, plus 2 times negative 2, so minus 4 on top. The magnitude of v squared is going to give me 7 squared plus 1 squared plus negative 2 squared. on the bottom, and then all that is going to be multiplied by v. So that gives me 12 on top over 54 v. And so if I distribute over v, I'm going to get 14 over 9i plus 2 over 9j minus 4 over 9k. All right, so let's look at our picture again. So I've got this entered here as angle or vector w, and if you look here, notice that it is in the direction of v, right? In the direction of our red. Oh no, I've moved c. Undo. Sorry. Oh boy, what have I done? I was just trying to zoom in. There we go. It's in the direction of c. U. The projection of u onto v is in the direction of v here, okay? And so it's exactly what you would do if you would cast the shadow of the blue vector onto the red vector. All right, the last thing we want to find is the vector component. Remember, that's going to give us a vector that's orthogonal to v. So let's plug into that formula. So the component we just find by taking u minus the projection of u onto v. And so 3 minus 14 over 9 is going to give me 13 over 9i. Negative 5 minus 2 over 9 is going to give me negative 47 over 9j. And finally, 2 minus negative 4 over 9 is going to give me plus 22 over 9k. And so let's look at that in the picture. So that's my vector here. And you can see if I'm afraid to rotate now. If I rotate this, it's, well, you can see that this black vector here is orthogonal to our red vector, right? So we've written our vector u, we can write our vector u as the sum of the purple vector and the black vector. In particular, those are vectors, one vector that's parallel to v and one that's perpendicular to v. All right, I want to do one last example of work. And so let me throw the formula up here. I'm going to switch slides. There we go. So if F is a force not directed along the line of motion, then the work W done by the force in moving from point P to a point Q is W equals the magnitude of the projection of the force onto the vector PQ times the magnitude of PQ. Now remember, the projection of F in the direction of PQ here can be replaced with cosine of theta times the magnitude of f times the magnitude of PQ. And that is just the same as f dotted with PQ. Now, depending on what you're given in a problem, one of these variations of this equality is easier to handle than another. Could be easier to handle than another. The picture that you want to have in mind is that you're moving, say, from point P to point Q, and you've got some, so here's your direction that you want to go, and here's your force F with an angle theta. So you want to think of casting that shadow of F down in the direction you're hoping to go. So that's my projection of F in the direction of PQ. Okay, and that's what it looks like to move in that constant direction. Okay, so let's try looking at an example. This is example 8 in your book. So we're going to try to close a sliding door. A person pulls on a rope. With a constant force of 50 pounds at a constant angle of 60 degrees. We want to find the work done in moving the door "12 feet to its closed position." Now I'm going to sketch a little picture here, but really you should just look at the picture in the textbook. So the idea here is we've got some sort of large barn door here, and we've got an open space that we're trying to move it. This is my 12 feet. And so I've got this rope hanging from the top that I'm going to pull at an angle of 60 degrees. So here's my force. And I want to move it from here, call that P, to the closed position Q. All right, so that's our goal. Now my formula says that work is the magnitude of the projection of F onto PQ times the magnitude of PQ and if you look at the second variation of my formula, that's going to be a little bit easier to work with here because I know the angle that I'm going. So cosine of theta times the magnitude of F times the magnitude of PQ. Okay, so cosine of theta, theta is 60 degrees, so cosine of 60 degrees. Magnitude of F, well, we're told that the force is 50 pounds. So my magnitude here is 50. And the magnitude of PQ, we're also given, we want to move a distance of 12 feet, so 12. Okay. Cosine of 60, this is one of those angles you should know. I always have to redraw the triangle. I have 60. 1 is the adjacent side. I have root 3 on the opposite side, and 2 cosine is adjacent over hypotenuse, so 1/2 times 50 times 12. These are real multiplication, not dot products, right? Maybe I should put them in parentheses so that's clear. That's going to give me 300, and then I need my units. These are feet and pounds. Whoops, not per pound. Feet dash pounds. There we go. Not squared. My goodness. Pounds. S. Okay. All right. When we get back to class on Monday, I am happy to answer any questions that you have, but you should get started on the activities that I've assigned you to complete for class on Monday and get started working on the WebAssign homework.